Okay, morning. Let's start lecture. Good afternoon. Okay. Okay, so let's start lecture. Okay, so I'm gonna wrap up a few loose ends on lines. Okay, and then we'll go into a new topic, basically specifically on parametric equation describing curves in 3D space. Okay. Okay, so in the previous lecture, I have covered a few examples for lines in 3D space. I have a few more, just a couple more to, and then a summary to wrap up this whole thing here. Okay, yeah. Okay, so let's take a look at one more example here. It's actually a fairly straightforward example here. Okay. Okay, say that we have a plane. So we have a plane and 2 points at here. What we're trying to figure out here is basically the relative relationship between the planes and the points. Basically, we want to see, for example, are the 2 points on the same sides of the plane, or are they on the opposite sides of the plane? Or maybe even one point is on the plane. Okay. So that type of things, okay? So let's take a look at this example here quickly. Okay? So we have a plane at here. Okay? So the whole point at here is, without actual plotting it, how can we mathematically determine where these 2 points are? Are they on the same sides, or one here, or even one point is on the plane, that kind of thing, okay? Yeah. All right. This is actually quite straightforward, because if you want to, first of all, if you want to verify whether the point is on the plane or not, we will basically substitute the point into the plane equation, right? And to verify essentially whether that point, the coordinates of the point, satisfy the plane equation or not. Okay, so let's do that. So we can plug this Q0 and Q1 into the plane equation. Okay. We're actually gonna we're only gonna plug it into the left side here. Okay, so if it's on the plane, then the left side will be the same as the right side. So let's do that. So if we plug the first coordinate into the left side here, we have a -1 plus 2 times 2 plus 4 times 2. So that gives us 11. Okay, so this is for Q0. If we plug it into the Q1, okay, the Q1 coordinates, we're going to end up with 1 plus 2 times 3, 4 times -1, and that equal to 3. Okay. So the left side, okay, for the 2 coordinates, one is 11, the other is a 3. Okay. So apparently, but neither of them are the same as 7, right? And the first one is greater than 7, and the next one is less than 7. Yeah. So, and this actually brings the question now, basically. What will be the relative relationship between this Q0, Q1, and the plane now? Okay, yeah. Apparently, see, when you plug it into the left side here, you get a number greater than 7, or you plug it in the left side here, you get a number less than 7. So this is very much like if you recall in 2D, let's suppose that we have a y equal to kx plus b, that type of equation, right? So that's a straight line equation in 2D. Okay. There's also a question very generally say, okay, how do you represent the area on the top of this straight line at here, right? So that's a question. Or how would you represent the region at the bottom of this straight line here? Yeah, you must have seen this kind of question, right? Yeah. So this is easy, you know, for the region on the top, you say, okay, this must be y greater than kx plus b. Okay, right? That's how you represent the top area. Okay. And same to this kind of question too. When you have a plane, okay, this is a plane equation. The plane separates the 3D in two halves, right? In two halves. Then the question will be, how would you represent the top half of the region, right? And how would you represent the bottom half of the region? So then, let's say, for example, in terms of this one here, and you will see, okay, the top would be what? X plus 2y plus 4z greater than 7. Okay, so that would be the top region here. Or the bottom here, it will be here x plus 2y plus 4z less than 7. So the whole 3D space can be separated into two regions. One is top and one is bottom, right? And you can represent that using this inequality at here. So back to this specific case, so one point give you 11 greater than 7, the other point give you a 3 less than 7. So that must mean one point at the top, the other point at the bottom here. Okay, so that's basically how you can determine the relative relationship, okay, for the points and the plane. And of course, then we're going to choose the second answer here, okay, the opposite side. Okay, so let's extend from here just slightly. Okay, if I have 2 points like this, okay, so the next question is, if we connect the 2 points, okay, connect the 2 points, we can construct ourselves a straight line. Then the question will be, what's the straight line equation? Where will be the coordinates for the intersection point between this line and the plane? Okay, so that's the second part of the question here. Okay. So, what will be the intersection point's coordinate? How do we find the intersection coordinates? Okay. So, first step you do, okay, so I just find the straight line first, right? That passing through this Q0 and the Q1. So that's simple because you have the Q0, Q1 coordinates given to construct a line. All we need is just a parallel vector now, so we can use Q0, Q1 as a vector, as this parallel vector to construct this line here, right? Okay, so we can see, okay, so this Q0, Q1 vector, okay, so that gives us using the Q1 coordinate subtract the Q0 coordinate, so give a 2, 1, negative 3. Okay, so that's Q0, Q1. Then the line, right, equation. Okay, you can write it down, the line equation now. Just you don't have to write just formula now. So x equal to, let's see if I pick the Q0 point for this location here. So it'll be negative 1 plus 2 times the parameter. Suppose I use a t. And then y will be 2 plus this 1 times t. And z will be 2 again plus, not plus, it's negative 3 times t. So this will be the line equation passing through the Q0 and the Q1. Okay. Yeah. So far so good? Yeah. Okay. So then we're ready to basically to solve the question, what's the intersection points between this line and the plane, right? So I think we actually probably dealt this kind of question before. x, y, z here basically represent is the coordinates on the line, right? It's the coordinate line. So when they intersect this plane, then that means that point must be on the plane, right? Must be on the plane, or meaning that point must satisfy the plane equation. So we can substitute these coordinates here, okay, into the plane equation. Okay? So sub this line equation into plane equation. Okay, so we have our plane equation here: x plus 2y plus 4z. So x is negative 2 plus 2t plus 2 times 2 plus t plus 4 times 2 minus 3t equal to 7. So one equation, one unknown t, and you can solve for the t value. End up with 1/2. Okay, and then sub the t value back into the line equation. So that will be the intersection point coordinates. Okay, so we end up with the coordinates. So intersection point. Okay, and end up with 0, 5 over 2, 1 over 2 at here. Okay, so that's the for this question at here, right? Yeah. Okay, so in this question, and obviously the line intersect with the plane, right? And it's pretty obvious because you have 2 points on the opposite side of the plane, and you construct the line, and it definitely will intersect the plane in here. Okay, yeah. So I want to ask you a general question in here. Okay, basically it's more of a just establish all the relationship. So if you do have a plane, okay, and you're giving a line, okay, so all you see is basically it's a plane equation and it's a line equation, right? Yeah. So so here's a question now. Okay, so given a line and a plane. Okay, given a line and a plane. What's the possible basically relationship between the line and the plane, and how would you verify that using the method here, basically, right? Yeah. So let's think about a possible relation. What's the possible relationship between a line and the plane?
The parallel.
Parallel. Okay. So basically the plane, the line is on the top of the plane, right? Or they never meet with each other. Okay. Yeah. What else? Intersect. I guess that's too obvious, right? What's the other? Is there any other?
In the plane.
In the plane, right? Yeah. So there's another possibility is in the plane. Okay. Now sometimes you can consider this in the plane more or less can be included as the parallel case. Okay. But mathematically they're actually quite different. Okay. Okay. So now if you want to try to verify this, right? Then how can we verify the 3 scenarios that we just said there? You can actually start by the most obvious cases here. So suppose you have, let's say, you have a line equation here. Okay, so you got the line equation now, and you got the plane equation. Okay, so I don't know what the line equation is. So it's x equal to basically x is some sort of a function t, and y is some sort of function t, for example, right? Okay, so this is probably is your line equation you'll be given, and plane equation. Let's say you probably given ax plus by equal to z cz equal to d. Okay, so that would be a plane equation. So this is basically what's given here, right? How can we make a quick decision to give us the relative relationship? So as we just did, in order to verify if whether they intersect or not, what you do is, or even if you probably already know for sure they intersect, so you can substitute the equation for x, y, z, or the line equation into these plane equations, right, into the left side. Okay, so let's say if I do this, right, if I plug this line equation, so whatever the line equation is, okay, into the left side of the plane equation. So I'll give you basically I'll give you two scenarios sort of here, okay? And then you tell me what does the result sort of here actually mean, okay? So let's say if I plug the line equation into the left side of the equation here, right? Okay, yeah. So case one, so what we'll get is once I plug it into this left side, what we get is we get left side equal to D. Okay, so whatever that line equation is, here, so doesn't matter what it is, so some sort of line. I plug it into the plane equation left side, and I get an answer which is a constant D. What does that tell you?
The line is on the plane.
The line is on the plane, right? So basically, see this, it represents the coordinates for all the coordinates of the line, right? So you plug all the coordinates of the line into the plane equation, you get the same answer, constant. So that's what basically means here. The line, okay, is on the plane or in the plane. Okay. So that's very easy to verify, right? So second case, let's say if I plug in to the left side and I got the left side, let's say equal to a constant, I'll call it E, but not the same as D. Okay? Yeah. So you plug it in, and you got a constant other than the D. Then what does that tell you? The line is, yeah.
So when you plug the equation, what value do you use for T?
I just still use the T.
Oh, and it cancels out in a given point?
That's right. Yeah. I keep the T. Okay, basically whatever the expression for the line equations, right? Yeah, you keep it as it is, then you plug it into, just like this, just like here, right? We plug this one into the plane equation, right? Yeah. So this one here, you got a constant other than the D here. I guess you probably see. So the line is what? Parallel. Okay. And the last case, of course, you plug into the left side, okay, and you end up with some sort of a expression which relates to the T, right? Yeah, and then equal to D. Okay. So now in this case, it's obvious. The line must what? Intersect the plane. Okay. Yeah. Okay, so that's the general relationship between the line and the plane. And to extend from here a little bit here, but I won't go into too much detail in here. Any questions before I proceed? Okay, yeah. Go ahead. What's your question? Parallel, basically, when you, for example, here, right? When you substitute the line equation into the left side of the plane equation, okay, you're gonna get a constant, but this constant is not the same as the plane equation's constant D. So basically, it's like the line somehow is actually somewhere else on another plane, which is parallel to the plane, right? You're looking for. Okay. Yeah. Okay. And this is also the next one here is also helpful. Is for you to have a clear, basically, what's the relationship between two lines, basically. Okay. So this is also something you should actually think about it. So I'll just write it down the three different cases here. When you have two lines, just think about what are the possible geometric relationship between the two lines. One is what? Pre-opposite of the two lines? Parallel, right? Or the other thing is the two lines actually is the same, right? Yeah. Or what? Skewed, right? So let's do that exercise. Good. Parallel, same, and then skew here. So basically what I want you to think here, I want to go into details here. How would you verify the three different cases given two line equations, right? So how do you know whether they are parallel, they are same, or they are skewed? Okay. You can use actually logical derivation here. You know, say, okay, they're not parallel, they're not the same, and they must be actually skewed, right? So that's one way to do it. Actually, it's probably easier to do it because you can easily show that whether they're parallel or not, or they're same or not. Okay, yeah, and then you can derive whether it's skewed or not. So try to think about these different scenarios here, right? And that could help you when you are doing assignments or question exams. Okay. So I will just provide a summary here before we move on. Okay. Those are basically some sort of a possible questions, okay, on lines. Okay, not necessarily on lines, maybe a combination. A little bit combination between lines and the plane. So the biggest category here often is to find a line equation. So you're given some information, and then you're required to find a line equation. So for example, you probably could be given very simple. Just give a point and a vector, right? And the vector parallel to the line. So that's the simplest scenario. Then you can substitute the point and the parallel vector to the line formula. You get the line basically. Or sometimes you're given a point, okay, and then you're also giving a line, okay, parallel to the line. So basically, you're asked to find a line passing through a point. At the same time, this line is also parallel to another line. Okay. So that's quite simple, because if you're given another parallel line, you can easily extract a parallel vector from the line, and then you can use the same parallel vector to construct this new line here. Or you're just being given 2 points, and now we just exercise. And or you are given 2 plane equations. Okay. So this is also pretty obvious when you have 2 planes. If the 2 planes are not parallel to each other, then the 2 planes will intersect. That intersection basically will yield a line, right? And how would you be able to derive that line? Okay. And we'll shortly actually show you one very quickly in terms of deriving a parametric equation. Okay. And here's another two possible scenarios here. So you're given a point, and then you're given the condition such that this line is perpendicular to 2 given vectors. Okay. So basically, you have a point in here. You got 2 vectors in here. Okay, and then you wanted to find a line that passing through the point and perpendicular to these 2 vectors. Okay. So how would you do that? And it's pretty simple, right? Use a cross product, find the cross product, and that'll be the parallel vector to the line, right? Yeah. Okay. Or just simply saying you're given a point, okay, and the line is perpendicular to a plane. Okay, it's very similar to the previous case. Okay, if you've got a plane, then you can get the normal vector. Then you can use the normal vector as the parallel vector to the line, right? Okay, so that's generally for looking for a line. Okay, I don't think that any one of them is that's not difficult. Now, if you're giving a line or some other conditions like in the plane, so maybe what you're looking for is try to find the distance from a point to a line. Okay, and that's also a very common question, and we actually went over one typical question with a variety of different solutions, right? Yeah. And now another one here could be find the distance from find the distance between two lines. Okay. So another possibility. Yeah. So this one is exactly the point that we just gone through here. If you're trying to get the distance between two lines, maybe you should actually quickly check the relative relationship between the two lines. Are they the same line? If the same line, then their distance 0. And are they parallel, right? Or are they skewed? Okay, so that type of things can give you an idea regarding this concept of the distance here. Okay, yeah. So these are fairly typical kind of questions for lines. Okay, yeah. And then we also exercise this now. Find intersection points, okay, between a line and a plane. Okay, so we just did that. So how do you find the intersection point? Or even just the question is if it actually exists or not, right? So, okay. And also you could be asked is, can you find intersection points between two lines? Okay, intersection point between two lines. Okay. And this is the same question basically. Is it really exist? Right? Because we just mentioned that when the two lines could be parallel. Right? When they're parallel, they never intersect each other. And when they skew, and they don't intersect each other either, right? Yeah. Only one case will give you this intersection points, right? Yeah. How would you solve that, or how would you prove that they don't actually intersect each other? Simply put it, basically, you equate the two line equations, right? You equate two line equations. So there are x, y, z, and you get 3 sets of equations. So we did that cat and mouse, but the cat and mouse is in a 2D, but in 3D you have x and y, z, right? Yeah. So basically you equate, you have 3 equations, but then you have to only have 2 unknowns. So you need to pick 2 equations out of the 3, and you solve for the 2 variables. Once you get a solution, you substitute in the third one. If they equate each other, that means they intersect. If they don't equate each other, then they must be either parallel or skewed. Okay, yeah. So try to look for a similar question in the assignments there. Okay, yeah. Okay, so that will be pretty much everything on lines and the planes. Okay, yeah. So any questions so far? Okay, before we move on. Okay, good. Okay, so let's move on in here. So we'll look at now a new topic, basically parametric representation. Okay. So instead of calling it line now, so I'm going to move it to a more general concept, curves, okay, in 3D space. And we'll look at how do we describe a curve, okay, in 3D space. And as you can see, we're going to actually use a very similar concept, parametric equation, okay, to represent a curve in 3D space. Okay, so that's the idea here. First of all, let's think about the curve. So here's a curve, say, given in a 3D space. Okay. So when you're talking about the curve in 3D space, and you can always relate that curve to some sort of physical meanings. So you can think of a curve as a trajectory of a motion of the moving points, right, along this curve here. Just like the way we derive the line equations. So we derive line equation by considering some sort of moving object with the constant velocities along a straight line, right? Yeah. So I can use a similar concept here. Then, if that's the idea, then we can all can always do is, okay, if I pick a point on the line, okay, which represent the coordinates, okay, of a certain moving point, and then you connect the origin to that point P, and you will get a so-called what? The position vector, right? Position vector. So if I use R to represent the position vector, then I can think of this basically if t is actually a time-dependent position, so at a different time instant, this point P is at a different location on the curve C. So I can use the position vector, which is a function of this t, right, to represent this position for the point P. That makes sense, right? Yeah. So then this r of t, right, it's a vector. It's basically x of t, y of t, and z of t. So that's your position vector at here. It has three components. It has x of t, y of t, z of t, and that ultimately basically give us an idea if we can somehow find an expression for each one of these x, y, z, okay, then we're able to basically come up with a expression or math equations describing this motion point P on the curve C, or basically the mathematical equation describing the curve C here. Okay, yeah. So that's the idea in terms of the parametric representation of the curve C here. Okay, yeah. So what we're striving to do is for any curve C. So let's try to see what will be a possible x of t, y of t, z of t, basically. Now what I show you here, mostly there isn't a very in this part here, there isn't a very clean or a precise way of deriving a solution in here. Okay, most of the time it's actually probably, you know, it's a result that you're supposed to probably will have to remember or something like that. It doesn't make sense. You'll see that it doesn't make sense. It's just that it's not like solving a question that you will go through 1, 2, 3, 4 and you end up with a solution. All right. So, okay. So I'll use examples. Okay, to illustrate the idea of a parametric representations for curves. Okay. So let's start from the first example here. Okay. Find basically find this parametric equation, okay, for the intersection line between two planes. Okay, so the moment you see this question, you probably will say, what does that to do with a parametric equation for a curve? Well, I mean, line equation is a curve right? It's a special curve, it's a straight line. So if you think about line equations here, what we have just like for example this line equation here, they're essentially just x of t, y of t, z of t, right? So this basically is a parametric equation in here. Now, coming back to this question in here. If I ask you differently, you know, forget about this lecture. If I just typical question, give you two planes, find the line intersection line here, like one of the summaries in the summaries there, right? So how would you do that, right? Okay, yeah. So I don't need you to solve it, but just before I move on to the way I will show you, just thinking about the way if I ask you given two planes, how would you solve for the intersection line? So you can always draw something in here. Right, so that's the intersection between the two planes. Okay. What will be the typical approach you can use to solve for a straight line? Okay, so great. So you have n1, n2. Okay, so cross product of these two. What's the cross product of these two normal vectors? That's right. They are. So basically, this is going to be the right? This is going to be this parallel vector to the line, right? Okay, good. So now you found a parallel vector now. And in order to construct line equation, you also need a what? You also need a point on the line. Yeah, good. So how do I find a point that line goes through then? Yeah, beautiful. So the line that goes through, the point the line goes through, must be a line somewhere here, right? Or must be a point intersected between the two planes. And there are infinite number of that. So you're basically looking for it's a solution, right? It's a solution to satisfy these two equations that are here. Okay? But in this case, you got two equations, three unknowns. And that actually proves that how many solutions? You have what? Infinite number of solutions here, right? From these two set of equations. So one way to, but we only need one. So one way to simplify is you can set one of the variables to be 0, right? And then you end up with some two variables now, and then you solve for the other two variables. And that'll give you basically a point, right? 1 point on it. That make sense? Okay? So then you can set, for example, set z equal to 0 and solve for x and y. Okay? Yeah. Okay, so the way you do this, right? You end up with a point, basically. Okay? A point on the line, basically. Okay? You end up the point or on the intersection between the two planes. Okay, so that's the typical way you will solve if you're given a question in assignments like that. But now I'll show you a fairly different way of getting a parametric equation here. Is basically maybe I should call it parameterize. Okay, parameterize this this question or this scenario. Okay, yeah. So you'll see what parameterize means, and I'll show you more examples here. So this is the idea I wanted to show you here. You see here, when you set z equal to 0, and you solve for x and y, you end up with what? All the point. It will end up with 1 point on the line, right? Okay. But the objective is actually you want to get an expression for what? For all the points on the line. That makes sense, right? And you also have learned that a parametric equation is basically three equations in terms of parameter t or some other parameters. Another fact is what? How many solutions for parametric equation for a line, for example? How many? Infinite, right? Yeah. So in this case here, so then I'll say instead of a set z equal to 0, I'm going to do what? I'll just set z equal to t. That makes sense? Right? Because this is a function of t, right? It's basically a part of the formality of the line equation, basically. Does that make sense? Right? So I'll just set z equal to t, and then we solve for the x and y. Okay. So you set z equal to, instead of 0, you set equal to t, then you solve for x and y. So what does that mean? Now basically means you plug this t, right, for the z. Okay. So plug it in, you get these two equations here. And now solving for x and y means now you treat the t as a part of this like a constant now. Okay, so just treat the t as if it's a constant now. So then you get x minus y equal to 4 minus 2t, 2x plus y equal to 2 plus t. Okay? Yeah. So you treat t as a part of this constant. Then you solve for x and y here. Okay? So you'll be able to get x equal to 2 minus 1/3 t and y equal to -2 plus 5 over 3t. Okay. So if you solve these two equations, you end up with this expression for x and y as here. Now, see, you end up with two expressions for x and y are completely in terms of this parameter t. So group back with this z equal to t. So that's basically your line equation. Okay. Yeah, it's basically your line equation. And this essentially, it's one way what we call to parameterize this case. So because originally here is you got two equations here. Now you turn the two equations, okay, into one set of a parametric equation here. So that's called parameterize this this case here. Okay. Does that make sense? Any questions so far? Okay. Good. So let's take more examples here, and then show you more examples in terms of how do we parameterize a different kind of equations. Okay, so let's take a look at now very common curves. X squared plus y squared equals a squared. So this is a very common curve. It's a circle, right? So okay. It's a circle with a radius of a. Okay. Now the question here is to find a parametric equation for the circle x squared plus y squared equal to a squared. Okay. Yeah. So how do we basically come up with a parametric equation for this one here now? Ultimately, you still try to do is try to think of this is trajectory. Think of this is a trajectory for some sort of a moving point P. Okay, so the P will move around this curve C at here, which is a circle in this case. How do we describe the motion of this point P, which essentially will sweep out a trajectory for as a circle, right? Okay. Yeah. So here's what I would do at here. Okay, I'll just draw, for example, draw a vector from the origin to the point P at here. Okay, from origin to the point P. Okay. And I'm gonna make some assumptions at here, because if I think of a motion point P on a circle, there could be actually, I'll show you different ways of describing the motion here. So here's the first case at here. Okay, suppose the P starts at point A. Okay, so where does it start? It starts at this point A at here. Okay, so A is this point. Okay. It started here, and it moves counterclockwise. Okay, it moves counterclockwise at an angular speed omega. Okay, an angular speed omega. So basically the point P is going counterclockwise motion. As you learn in dynamics, it's a unicircle type of motion at here, right? If you look into the 3D, essentially this is the axis of rotation, and the point P is going to rotate at omega angular speed. Okay. Yeah. Okay. So, and now we give actually a specific physical meaning now to this curve. Instead of just x squared, x squared plus y squared equal to a squared, right? Okay. So angular speed omega meaning what? Let's say it starts at a equal to here. Basically means that's your t equal to 0 moment, right? Okay. Yeah. As it going basically away from this x-axis, okay, and it'll trace out an angle theta, right? Yeah, between this OP and the x-axis. Okay. Now, from now on, actually, from way before this, when you basically consider the positivity of angle theta, theta is always measured from what? From where the line is to the x-axis, right? And theta is always positive when it's counterclockwise. Okay? Yeah. So that's how you define your angle theta. If it goes clockwise, then you consider as instead of positive angle, you consider as what? Negative angle. Okay? Yeah. So in this case here, I have a theta here. But it's going at a constant angular velocity. So that basically means for any other time moment, the theta equal to what? Omega times t. Very good. Okay? So this will be, at this moment, it's omega t. Okay? It's omega t. Okay. So now you see, at this moment is omega t at here. Then we're looking for is a parametric equation for the point P. Well, parametric equation is basically the coordinates for the point P, isn't it? Right? You know, x of t, y of t, that basically is the coordinates for the point P. So what is the coordinate for the point P at this moment? What's the coordinates for the point P at the moment? So you have A at here, and then you have theta at here. So coordinates basically means these two, right? These two at here. So x equal to A times cosine theta, or A times cosine omega t. And y equal to A times sine theta, or sine omega t. That's the coordinates for the point P. So apparently see both x and y, they're a function of t. Okay? Yeah. So now you look at this one here. What's the expression? The expression is exactly in the parametric equation format, right? Exactly in this format here. Okay? Yeah. And is this the parametric equation for the circle then? Right? So basically, is this the parametric for circle, or is this the parametric equation describing the trajectory, which is the circle? Okay? How would you verify that? How would you verify that this is the parametric equation for the circle? Yes, that's right. So verify, all you do is you square each one and add them up, and what is it equal to? A square, right? So that's exactly the circle. Okay. So which means this is a legitimate parametric equation for the circle that you're looking for. Okay. But you still have to be very clear though that this is a parametric equation, and it describes a certain type of a motion at here, right? It describes a certain type of motion. What type of motion? Start at the point A and moving counterclockwise with an angular speed omega. That make sense? Yeah. So if you substitute omega with the different values, apparently you see you'll get a different parametric equations for the circle, right? Yeah. So that still tells you parametric, there are infinite solutions for the parametric equation for the circle right here. Okay, and that's so typical. So if I ask you slightly different, let's say if I say, okay, so I'm gonna try a slightly different motion. Okay, slightly different motion. So in this case here, suppose that it starts at A, still start at this A here, but it's gonna move clockwise, okay, at an angular speed omega. So now instead of going counterclockwise, it goes clockwise now. Okay, go clockwise. Now, what will be the parametric equation now? Okay, and you come up with the parametric equation. Use a very similar approach at here. Okay, use a very similar approach. Okay, so basically it'll go this way. Okay, and as it goes around, it will trace out the circle again, right? It'll trace out circle again. Okay. So if this is the point P, this is t equal to 0. At any other t time moment, the point P is over here. Okay, and that will be the theta now, right? That will be the theta. Okay. So before I write it down, I wonder if anybody can give me a possible solution at here. So then theta is still moving at a constant angular speed, but this is gonna be, but it's just that it's actually going this way, right? It's going this way instead of going this way. Okay. So remember what I said just now. How do you define the positivity and the negativity for theta? Yeah, David.
It goes counterclockwise it's positive and clockwise it's negative.
Very good. So if I go clockwise now, the theta is, instead of omega t, we should call it what?
Minus omega t.
That's right, negative omega t, right? Negative omega t, okay? Yeah. So you basically, actually all you need to do, okay, is x of t equal to a times cosine what? Negative omega t. And y of t equal to a times sine, okay, negative omega t. Okay? So that will be the parametric equation, or the coordinates. This is the coordinates, right? That will be the coordinates for the point P, okay, as it's moving clockwise, okay, starting from position A. So use your trigonometry property. Cosine negative number is always what? Okay, cosine omega t. But sine negative number is, sine is an odd function, so it's negative sine omega t. Okay. Does that make sense? Now you probably will see, is that still the parametric equation for the circle? Well, you can still try to verify, right? You can verify here. How do you verify? To take the x squared plus y squared, and you're still going to get a squared, right? Yeah. So basically, the point I'm trying to give it to you is, we're not just trying to cover a mathematical concept called parametric equation. Behind this parametric equation, there's somehow there is a physical meaning, always related to that. Okay, it's a motion. Then often in time, it's between position and velocity. It's a type of motion it's describing. Okay, so the parametric equation describes certain type of motion at here. Okay, so I'll write it down at here. Okay, so parametric equation, okay, describes certain motion. Okay. Okay. So look at my lecture notes here. I'll give you this. This is a scenario here. What if we start at a B and going counterclockwise with omega, right? Start at B going counterclockwise, and what will be this x of t, and what will be this y of t? Okay. Yeah. So check it out yourself. Okay. Yeah. Okay. So that's the circle centered around the origin, right? There could be very well another situation, basically a circle centered around x naught, y naught. Okay? Yeah. So that could be another situation in here. Now for this one, in Cartesian coordinates, the Cartesian equation is x minus x squared, x naught squared plus y minus y naught squared equal to a squared. Okay? And that's basically one single expression describe this circle. So as you can see, this one single equation really doesn't tell you anything about the motion, right? It only tells you the trajectory. It doesn't tell you anything about the motion. So if I wanted to parameterize this one here, so you have a very similar basically approach, but in this case here, because there's x naught, y naught, okay, I'll just write it down here, and then you'll see it's x naught plus a cosine, let's say omega t, and y t equal to y naught plus a times, okay, sine omega t. Okay, so that's one possible solution for this parametric for this circle here. So basically, it started A, and then going around the circle with angular speed omega. Okay. And you can verify, right? You can always verify. In this case, how do you verify? It's the same thing. You sub the x and y into this equation here, and you get the same answer as the right side. So that basically it's verified. Okay. Yeah. Now this is a parametric equation, right? And I'll show you a little more there. Okay. Okay. Before we move on, let's say maybe another thing we get used to is to write down a parametric equation. You can always write down this x of t, write down the y of t, and the z of t for sure. Okay. And the other way of writing parametric equation is you can basically just write down the position vector r. That right is x of t, y of t, and z of t. Right. That's something this. As I mentioned in the first lecture, you can also write it in terms of I hat, j hat, okay, and the k hat. Okay. So then, for example, for this particular circle, then we have basically x naught plus a cosine omega t, okay, I hat, y naught plus a sine omega t, j hat, and then there's no k hat, so that's just 0. Okay, so different way of expressing it. It's just different way expressing this parametric equation here. Okay. Yeah. Okay, so one more in here. Let's say here is a ellipse, right? So x squared over a squared plus y squared over b squared equal to 1. So this is an ellipse. Okay. If you draw it out, it's actually an ellipse centered around the origin. Okay. The a will be here, the b will be here. Then can we come up with one set of parametric equation describing this ellipse at here? Okay. So as I said, there isn't a sort of a systematic way to derive parametric equation. It's often in time it's based on experience and based on maybe a little bit derivation, but it's not really systematic. So for example, in this case study here, you can think of this to compare this with the circle, right? Ellipse is a circle is a special case of ellipse. So if this is a square, then it's become a circle, right? Yeah. So then in this case here, I can see x equal to a cosine t. It's just like what we did in the circle. But then the y at here, okay, will become a b, for example, sine t. Okay, b sine t. So, and that's a possible solution, right? A parametric solution for this ellipse. In this case here, it starts at a, okay, and then moving in this direction at here. Okay, so that is one solution. And of course, you can use 2t, sine 2t like that, so then no problem at all. Okay, yeah. Or even you describe as a different motions starting here but going counterclockwise, or starting here and going clockwise or counterclockwise, whatever. Right? Okay. Yeah. But just for your own interest here, in general, okay, this is actually not parametric. In 3D, okay, sorry, in 2D, okay, here is the general Cartesian equation, okay, for ellipse. Okay, this is in general. And I'll actually, at the end of the lecture, without really deriving it, I'll give you a parametric equation for circle in 3D. Okay. Okay, so that's one example here. So it covers the circle, covers the ellipse. Okay. So now let's look at another one here. Okay, very general curve. So y equal to x squared. Okay, y equal to x squared. Okay, that's a very typical curve. So it's basically a curve look like this, right? It's a parabola type of a curve. Okay, yeah. How do I get a parametric equation for this y equal to x squared? Very simple. Okay, one solution is you simply let x of t equal to t. Okay, and then the y of t will become what? T squared. Okay, t squared. So that's one possible solution, right? For this parametric, to parameterize this y equal to x squared. Okay. Now let's go into this a little bit deeper here. So this is a parametric equation, but remember what I said, behind every parametric equation there is some sort of a motion, right? Can be described. Okay. So look at this parametric equation here. What kind of a motion would that be able to describe? Or even just basically think about the actual moving points. Okay. Okay. So in this case here, let's say if my t starts at 0 and goes to t equal to 1. Okay, goes to equal to 1. And what exactly, based on this parametric equation here, right? Based on this parametric equation here, how would I basically now draw the motion now? When t equal to 0 here, it's 0, 0, so it's here, right? Here. And then when t equal to 1, where is it? It's at 1, 1, right? It's here, okay? And it's going basically along this curve. So from here to here, so that's basically the motion here. If t keeps going, then you would expect that it'll keep going up, right? Okay. That makes sense? Okay. So now I'll give you a slightly different situation now. Okay. So this is A point, this is a B point. Okay, suppose that the A here is 1, 1, could be of course 0, 0. Now instead of going from B to B to A, okay, like the first case here, we go from A to B. Okay, we go from A to B at here. So from A, starting at A, and end at B. But you still want the point to be along this y equal to x squared trajectory. Okay? Yeah. If that's the scenario, can we still use this parametric equation? Apparently not, right? Then what would be a parametric equation for the case that we just described here? See what I'm saying? So basically t is 0 here and t is 1 in here. So t start at here but end at the B. Okay? Instead of t equal to 0 and t equal to 1 like this. Okay? What would be a possible solution for this scenario? So t equal to 0 at A and t equal to 1 at B. So you need to figure out an x of t, y of t, okay, and satisfying the exact given condition that here. Anybody? Yeah, David?
would it be x of t equals 1 plus or 1 minus t, and then y of t equals 1 minus t squared?
Yeah, exactly, right? So let's verify this, right? Let's verify if this is right or not, okay? Verify basically means you need to have two things satisfied. One is satisfy the given conditions that are here. At the t equal to 0, plug a t equal to 0 here. What's the x, y coordinate? 1, 1. That's good, right? At a t equal to 1, substitute here. 1, 1, 0, 0. So that's 0, 0 at the b. So perfect. So it satisfies the position a, b. And then you verify, does that satisfy the curve y equal to x squared? And it's pretty obvious because your x is 1 minus t, y is 1 minus t squared. So it's the original curve, the trajectory, right? So that's the idea for parametric equation. I'll give you another one shortly here, okay? You have to come up, sometimes you have to come up with a parametric equation that actually describes the direction, the motion that you're looking for, okay? So this is particularly true for maybe a few lectures down the road when we learn integrations along certain curves or along the trajectory, okay? The direction matters in that case. Okay, so a couple more examples. Okay, so let's see here. This is another one here. Okay, so this is example. Not really ask you to derive. Yes.
So in the last part,
yeah.
How did you get 1 minus t and 1 minus t whole squared?
How do you get it?
Line of thinking.
This is exactly the point I'm saying. There is no very systematic way I can tell you. Okay, you follow this, you'll come with minus 1 minus t, right? And a lot of the time it is experience, or it is some sort of aspiration maybe. So you look at this this one here. So this is 0, start at 0 and 1, end up at a 0 when t equal to 1, right? So that how do I put it? That basically one of t satisfies the given conditions that are here. So there's not really it's like you follow A, B, C, you end up the 1 minus t basically, right? Yeah. So I'll show you an example. You'll see what do I mean at it here. Okay. Yeah. After some practice, you'll get to this point actually quite easily. So the next one is more just illustration, not really a derivation in here. Okay. I'll give you a parametric equation. Okay, so this is the parametric equation: x, y, z, x of t, y of t, z of t. Okay, yeah. Before I tell you what it is, but let's examine this parametric equation a little bit. Okay, and then you actually will be able to understand what it is. First of all, forget about this last z of t here. If you just look at the first x of t, y of t here, what does the x of t, y of t describe? We just learned circle, right? It's a circle. So if you start at t equal to 0, and after 2 pi, basically it'll come back to itself, right? Okay, it's a circle. And what is the z component now? It's bt, right? It's bt. Basically, if you only consider the z of t, you start at 0, starting at z equal to 0, and when t keeps going up or keeps increasing, then the z keeps what? Going up, right? So now you think about it. So you have an x and y, and you have a z. So the x, y always going around and around and around, but in the z, every time it'll keep what? Going up. So basically, if you start at one point, every time it goes. What is that? What does it trace out? A spiral, right? Not a cylinder. It's a spiral. It's a curve. Cylinder, cylindrical. There's a surface. So it's a spiral, basically. Okay. Excellent. So, and that's basically illustrating what it looks like. The spiral. It's a spring. This is actually a very useful curve in many natural objects here. So this BT, for example, this BT at here, if you think about it, right? If you think about it here, So 2 pi, it comes back to its original starting point, right? But the z will go up so 2 pi t, right? So it goes up. It goes up by 2 pi t in the z direction for every circle, isn't it, right? Yeah. So this one here is actually called, okay, a pitch. Okay, it's a concept called pitch. And you all have dealt with screws. Okay, when you put a nut on it, you twist the nut one turn, the nut will go a certain distance, isn't it, right? Yeah. That distance is exactly called what? The pitch. And the curves, okay, basically the thread on the nut is a spiral curve. Okay, yeah, spiral curve. And same thing when you feel mechanical, you learn the gear and something else. There are also many curves, okay, that's described by this spiral, and we actually call it a helical curve. Okay, helical curve. Okay. So the value b at here, okay, the b actually describes how fast, right, it'll go up or down, right, along this axis of rotation. Okay. Good. So see one more example here. Okay, so this is actually this example is very important. This example I used it some years ago as part of the midterm question in here. Okay, so we will I'll give you a few points. Okay. So P, Q, and origin O at here. Okay, origin O. Now, suppose you are going to do this. You're going to start at the origin O and then go to the P, and then from P you go to the Q. Okay. So basically, you trace out 2 straight lines. Okay, using the given points. So we can call this is a curve C1 and this is a curve C2. So the question here is write down a parametric equation for the curve C1 and C2. And that's actually part of the question we'll ask for. You know, the first step, you're going to have to write down the parametric equation for C1 and C2. So this is the point at here. I'm actually doing the student ask how would you derive, right? There's really no derive. It's more often in time it's you write it down, that's it, right? It's based on practice, based on your experience at here. Okay, but it sometimes does require a little bit skill though. Okay, so let's look at the C1 in here. First of all, C1, which plane is it in? XY. Okay, so if it's in XY. That means I'm looking for x of t, I'm looking for y of t, I'm looking for z of t, but then the z of t must be 0, right? Okay. Okay, so from origin to the P1, it's a straight line, right? It's a straight line. Okay. Now, if it's hard for you to imagine, maybe let's just put it in a regular xy planes, okay? Right? In a regular xy plane. In a regular xy plane. What's the straight line here? It's from origin to here, right? So this. Okay? Yeah. Now, if you're not being asked to derive parametric equation, so then what's this trajectory? The equation for this trajectory is what? Y equal to x, right? Y equal to x. Okay? Yeah. Now you actually, probably from here it's much easier now. If you're going to derive a parametric equation for y equal to x, so what can you do? Maybe what? X over t equal to t and y equal to t equal to t, right? But does that satisfy the actual motion, right? Actual motion basically means when t equal to 0, you are at 0, 0. At t equal to 1, you're at what? Where? 1, 1, right? Yeah. So you look at your substitute here. That's exactly what you're looking for, isn't it? Right? Okay. Yeah. So the thing that you've got to be careful at here is if this is not 1, 1, right? If this is not 1, 1, okay? If this is, let's say for example 2, 2. then you can still use tt, but what would be the range of the t now? See, for example, here, when I use this one here, right, it's pretty natural that the t goes from where to where? If I write it down here, the t goes from 0 to where? To 1, right? But if your coordinates, it's a p, okay, if p is 2, 2, 0, okay, it's a 2, 2, 0, then you can still use the parametric equation, but then the t will actually go from 0 to what? To 2, right? To 2, okay? Yeah. Yes, you can. Absolutely. Right? Yeah. So that's basically the question here. What if I use x of t equal to 2t, y equal to t equal to 2t, and z of t equal to 0? Then what's the range for the t now? For this case. For this case here. Goes from 0 to 0.5. Yeah. Okay? Yeah, forget all this. Okay? Does that make sense? Yeah. So last one here for C2. Okay, for C2 here. C2 goes from P to Q, right? From P to Q. Let's deal with the most obvious one. What's the common things between P and Q? X and Y, do they change? They don't change. So if X and Y not change, then what's the X coordinate? 1. That's right. Y of t, 1. So only the Z is changing, right? And Z goes from 0 to t. So I guess you can still use the t then, right? But then the t has to be what? 0 to, the range for the t is what? 1. So if you choose z of t is 2t, then the t will be 0 to 0.5. So that's the point I'm telling you. For parametric equation, not only the parametric equation, but also the range, the t, also needs to satisfy the actual motion here. Okay? Yeah. Okay, good. So that will be all mostly about the parametric equation. Okay? Yeah. See you next week.